A beam of length 6 meters is simply supported at its ends and carries point loads of 12 kilonewtons and 10 kilonewtons at a distance of 1 meter and 3 meters respectively from the left support. Given a modulus of elasticity equals 200,000 Newton per millimeter squared, and an moment of inertia equals 85 million millimeters raised to the fourth power, which of the following nearly gives the deflection under the bigger point load and the smaller point load. To solve this problem, I'll be using the method of virtual work for beams to solve for the deflection under the bigger and smaller point load. So by solving for the reaction using statics, you'll get these values. We proceed formulating our moment equation. So let's try to consider the left-hand section of the beam. Going from a distance of x at the left support, we have our first moment equation that is equal to 15 kilonewton times the distance of x, which is the moment arm distance. This value holds only when x is between 0 and 1 meters. And for second moment equation, we have 15x minus the 12 kilonewton force times the moment arm distance of x minus 1 meters. And this equation is only valid for x that is between 1 meters and 3 meters from the left support. And for our third moment equation, we have 15x minus 12x minus 1 minus the 10 kilonewton force times the moment arm distance of x minus 3, which only holds true for x that is between 3 and 6 meters, going from the midpoint to the right support. For the next step, we will place a unit load on the point of the beam where the bigger point load is located, which is at a distance 1 meters from the left support. Now solving for the reaction using statics, this has a value equal to 5 over 6, and this one has a value equal to 1 over 6. Now cutting this section of the beam, considering the left section, we can create our virtual moment equation. So we have 5 over 6 times the moment arm distance of x, and this only holds true for x that is between 0 and 1 meters. And for second and third moment equation, we have 5 over 6 times the moment arm distance of x minus the 1 unit load times its moment arm distance of x minus 1, which only holds true for x that is between 1 and 6 meters. For the next step, we will use the formula for the virtual work on beams, that is the integral of the product of the moment equations dx divided by the flexural rigidity over the entire length of the span. So since the flexural rigidity can be factored out, this can be simplified into this formula. So we have the flexural rigidity that is equal to 200,000 times 85 times 10 raised to the power of 6. And then we multiply this by the integral of the product of the moment equation. So starting the first moment equation between 0 to 1, we have m1 equals 15x and small m1 that is equal to 5 over 6 x. We add this up to the next integral between 1 to 3. So we have m2 that is 15x minus 12 x minus 1 multiplied by m2 that is equal to 5 over 6 x minus x minus 1, and this has the differential operator dx. And then we add this up to the last integral between 3 to 6. So we have M3 that is equal to 15x minus 12x minus 1 minus 10 times x minus 3 multiplied by small m3 that is equal to 5 over 6x minus x minus 1 dx. And since this integral has a unit of kilonewton meter cube, to convert this into newton millimeters cube, we multiply this by a factor of 10 raised to the power of 12. Once we have our equation, let's put that into our calculator. So beginning with the first integral, let's store this into our first variable, that is in variable a, and then we add this up to the next integral, and then we store this variable in a, and then we add this up to the last integral, and once we have our integrals, we multiply this by 10 raised to 12 divided by the flexural rigidity of 200,000 times 85 times 10 raised to the power of 6. We get our final answer that is equal to 2.2549, which is closer to 2.26, which is letter B. And for the next problem, to solve for the deflection under the smaller load, we will place our 1 unit load in the same point where the smaller load is applied, which is 3 meters from the left and right supports. And by symmetry, the value for the reaction at the support is just equal to 1/2 of the unit load, which is just 1/2. Now this moment equation, actual moment equation won't change, only the moment equation due to the unit load would change its value. So for the first moment equation, by cutting this section, considering the left segment, we have the 1/2 force reaction multiplied by moment distance of x, and this is only valid between 0 and 3 meters from the left support. And for our second and third moment equation, this is equal to 1/2 of x minus the moment induced by this 1 unit load, that is equal to 1 times x minus 3 meters, and it is only valid for values between 3 and 6 meters of x. And then formulating our vertical work equation, we have m1 equals 15x and small m1 that is equals 1/2 of x dx between the interval from 0 to 1. And in doing the same to the rest of the integral, and then we input this into our calculator. For the first integral, we store this to the variable a, and then add this up to the next integral. And then storing this to the variable a, we add this up to the last integral. We have 71. For the value of this integral, we multiply this by 10 raised to the power of 12 divided by the flexural rigidity of 200,000 times 85 times 10 raised to the power of 6. We get our final answer that is equal to 4.18 millimeters, which is letter A.